Welcome everybody to another conversation. For the TLC today, we're going to talk to Dr. Elea Feit. She's a return guest with us today, and super excited to have you back, Elea. Really excited to go a little bit more into the stats talk that we started a couple of weeks, quite a few weeks back now. I don't know if you were able to attend, but we had Chad Sanderson and Matt Gershoff answer some questions related to testing statistics, and then we wanted to kind of go a little bit deeper, and you were graciously willing to help us out with that, especially for those of you who don't know. Dr. Feit is how do I describe the way you do statistics testing or teaching in college and how it's different? Because I know, like, we didn't know anything about experimentation and A/B testing, website testing, and the marketing effects of it when I was in school. And
engineers have been taking classes in experimentation for a long time. So I took one of those classes when I was getting my master's degree in industrial engineering. And then I became a business school professor. I build like these kind of crazy, complicated Bayesian models often for online, clickstream type data. And then about 7 years ago, I decided to develop a course in A/B and multivariate testing, focusing primarily on the digital space. And I teach that at the Wharton School with the full-time MBA program there, and here with the MS Business Analytics students. So slightly different, one more business-oriented audience, one more technical audience. But I teach a full semester course in A/B and multivariate testing. Like the very first day, we explain what an A/B test is, and then the second week, we talk about frequentist stats. The third week, we do a deep dive into like picking response variables and a bunch of kind of, I hate the word softer things, but less technical things, more kind of, how do you pick a low funnel measure or a high funnel measure? And then in week 4, we actually do the Bayesian analysis of A/B tests. So I've taught both Bayesian frequentist methods for a long time to both more business-oriented people and more technical people. So you can check out the class, it's Marketing 607 at Drexel, and it's Marketing 669 at Wharton.
And seriously, nobody would regret taking Elea up on that, because one of my favorite things about you, Elea, is that not only do you understand it, but you can explain it in a way that everyone else can understand. So
I try. We'll see how you're gonna you're gonna grill me for the next hour, so we'll see how it goes.
All right. Well, with that,
I like to start. Can I ask a question to start?
Please. Absolutely.
What is a statistic? Does anyone know what a statistic is? You could type it in the Slack. You could just unmute yourself. Does anyone have an idea what a statistic is? So I'll answer it. A statistic is a number that describes another set of numbers. So a statistic would be like the average. The average describes the central tendency of a bunch of other numbers. And like the standard deviation describes the variance, or how much bouncing around there is in that other set of numbers. So I kind of joke that like a statistics class, we would just learn different numbers for summarizing other numbers. That's not what we typically learn in statistics class. We actually learn about statistical inference. That's the focus in statistics classes. Does anyone know what inference is?
Elea, there's some answers coming in through your Zoom chat too.
I can't see the Zoom chat.
That's all right. Christina says that statistics are a measure of the whole.
Yeah, it's some kind of measure of that other set. That seems like a very reasonable description. So statistical inference, does anyone know what that is?
Come on, guys. I know you know. Inference, the assumption based on a set of measures. Thanks, Dylan.
Assumption? I don't... Yeah, I think I see where you're headed with that. No, I see where you're headed with that, Dylan. It's like It's basically, can we come to a conclusion from the data that we have? What I like to say, to make it really simple for students, it's, do we have enough data to come to a conclusion?
Yep.
So yeah, I wanted to start out with those two. Statistic is a number that summarizes other numbers, and inference is, do we have enough data to come to a conclusion?
And let's drive that one home a little bit, because I want to make sure you guys understand how this relates to A/B testing. Because every time we run a test, what we're doing is gathering the data, the statistics that help us understand and make a decision. And how do you know you have enough data, enough information to make a decision? And that's where the statistical inference comes in.
Yeah, so for instance, if you have a data set that's individual users and whether or not they converted. So that's actually numbers. It's zeros and ones. So as mathematicians, we like to make those zeros and ones. 0, they didn't convert. 1, they did convert. So you have this set of numbers. When you compute the conversion rate, you're computing a number that describes that other set of numbers. So that's a statistic. And then statistical inference is like, do we know what the true underlying conversion rate is? And I start out an example in class, like say you were hiring a salesman or a saleswoman, a salesperson, someone to sell stuff. So you're hiring that person, and as part of the interview process, you have them make 3 sales calls, and they convert to customers. And then you bring in another candidate, and she talks to 3 people, and she only converts 1. Do we think the first salesman is twice as good as the second salesman? That's what the means tell us. Like, one was a 2/3 conversion rate and the other was a 1/3 conversion rate. Do we have enough data to make the conclusion that we should hire the first one and not the second one? That's statistical inference in a nutshell.
Right, and like Tim's pointing out on the TLC Slack is, we don't really ever know the true conversion rate.
Right, and so inference is about trying to figure out, is the first salesperson better than the other? Do we have enough data? How confident are we that this one is better? And that is also never 100%, but it could be like, well, there's a 99% chance that this first salesperson is better than the second salesperson. I'm trying to catch up to what Dylan wrote on the Slack chat. Depends on what the average order value plus the lifetime value of the sales.
He's adding more data.
Oh, you're making it extra complicated, Dylan. Let's walk before we run. That's my approach anyway. Okay.
Well, speaking of walking and running, the question that we didn't get to last time, and that has come up repeatedly on these conversations and on the Slack, has to do with everybody's favorite question, Bayesian versus frequentist. What is the difference? Some tools use Bayesian, some use frequentist, and there's a big debate in the industry about which you should use. Rather than answering that question, can you just help everybody understand what is the difference between the two approaches?
Yeah. So they're two completely different sort of underlying philosophies about how we should make inference. And they're just completely different, just completely different. Like when I teach Bayesian, intro Bayesian methods, I usually say, forget everything else, just think about this for a while and just put the other stuff aside and do not try to relate the two. And the thing that makes this extra tricky for people is that at the surface, they seem very similar. In fact, the mechanics are almost exactly the same. You often get the same answer because they're both good inferential methods. So they both tend to come to the same conclusions with a few edge case exceptions, but mostly they come to the same conclusion. I like to think of it like religions. Most religions come to the golden rule. We should be nice to each other. We should be fair and kind, but they have like completely different sort of backstories about why they get to that conclusion that we should follow the golden rule. the same is true for Bayesian versus Frequentist. They are like completely different under the hood, but kind of feel very similar at the surface level. So
and come to very similar results.
What?
And come to very similar results.
Yeah, and so I think people, this whole Bayesian versus Frequentist, well, I'll just disclose, I am like deeply in my heart a Bayesian. I also love internal combustion engines for cars. And I will never, ever buy like an electric car. I'm just not into it. It's just not my thing. And I'm a Bayesian, and the frequency stuff is just not my thing. So that's just full disclosure. But I get that, like, in the end, they're both cars. They both get you where you want to go. They both have a steering wheel. They both have an accelerator pedal. At the surface level, they seem the same. But like, I'm just one of those girls who likes to get under the hood with the internal combustion engine. All right, so your question is, what's the high level difference? So so that all of that was to say, we shouldn't make much of these differences. Like, we're kind of overhyping it, but I'll try to directly answer the question. So under Bayesian inference, you start with prior beliefs, which would be kind of like, what are the range of values that this conversion rate is likely to take? And if my conversion event is click through on a home page, like, I don't know, I think that's probably going to be at least 50%. And it's probably not going to be 0, and it's probably not going to be 99. So I can kind of say, this is sort of what I think the conversion rate might be. And I start with those beliefs, and then Bayesian inference takes data and combines it with the beliefs to come up with the new revised beliefs. So it's this process of, I have starting beliefs, I do some math, I up math on data, and then I update those beliefs to get that's called the posterior. We have lovely posteriors, all of us Bayesians. That was just a little
A little stats humor.
But prior, and then we update with the data, and then we get these posterior beliefs. And then once we have, actually the cool thing about Bayesian is that the prior and the posterior are kind of the same. There's like this beautiful symmetry to it. So I can take priors from a previous data set and update those. Again, I can go through this process iteratively. And that's why you see the Bayesian methods being used for bandits, because the updating is just like, that's just part of the process. So that's Bayesian.
So hold on, before we go to frequentist, let me clarify, make sure that we get this. So the priors, you said, are basically some ideas that you have about what to expect. Are those ideas based on, or beliefs based on evidence? For example, the average click-through rate of a hero image on the home page, or are they just gut?
They usually should be just gut. One way I like to think about priors, first of all, you can set your priors that I'm not really sure. So you can say any conversion rate between 0 and 100% is equally likely. I don't know. I don't know anything here. And what will happen is, as soon as you get the data, those will change very quickly, and the data will. So in some sense, if you have a reasonable amount of data, it doesn't matter what your prior is. But the best way I've heard it described, there's a Bayesian statistician named Michael Betancourt, and he says, tell me what observations would be so weird that you would think there's something wrong with the data collection. And that would be outside of your prior, because it would be so weird. And he works with like scientists, lab scientists. He says, what's the value you'd get for this measure that would be so weird that you'd go back and ask the lab tech, what the hell happened here?
Sure.
So they usually are gut beliefs at the beginning, or so the other thing I've done is take like, we're going to talk about runtime calculation in a minute, but in order to do runtime calculations, I've taken like kind of what's the range of past test results I've seen, and that becomes my prior to do Bayesian runtime calculation. So it can be a combination of gut, scientific knowledge, physics, like literally like this can't happen.
Sure. So
that shouldn't be in my prior. It's all of that stuff together. The prior is supposed to summarize everything I know.
Okay, and Tim's asking, so the posterior becomes the prior? And then he asked, wasn't that the original way Bayesians approached things? Always started with 50-50 and then adjusted the prior?
So the first question, the posterior becomes the prior, is backwards.
That's what I
The
thought.
prior becomes the
Becomes
posterior. Beginning data.
Unless you start
end.
with, you don't know, because then it adjusts, right? The prior
Well, that's still a prior. I don't know, or I'm
Um,
not sure, is still a
still a
prior.
prior.
I start with that, I add some data, then I get the posterior, and then that posterior can become the prior for the next analysis.
I think
so maybe
that's what he means. Yeah.
That's what he means. Okay. Yeah, got it, Tim. And did people always start with these, like, I'm not sure kind of priors? Yes, that was like kind of that. There's a few sort of modern Bayesians who were like super against that. And from a business perspective, I'm kind of against it. Like, if you have knowledge, like for instance, click-through rate on a display ad, that ain't 50%, that ain't 40%, that ain't 20%. It's something less than that. And so why wouldn't I kind of incorporate that into my prior? Seems like a reasonable thing to do. So I've always advocated, like, you know, business is a combination of data and hunches. So why wouldn't you start with not hunches, but like, I have a little bit of information about this setup.
Apply your expertise.
Also, yeah, I think that's all I'll say. I have one other idea in my head, but I think it's too much. But I'll say it anyway. You had said, could you base the prior on, say, averages? It shouldn't be, the data that you use to update shouldn't be used to set the prior. And when you do that, there's a name for it. It's called empirical Bayes, which I think is a really bad name for it. I call it cheating and using the data twice. You shouldn't incorporate any information from the present data into the prior, because then you're using the data twice, and that's kind of cheating.
So when I say the average, I mean like the average click-through before you run a test, before you ever.
Yes, that would be perfect.
That's a prior.
Like, and also look at the range. Like, on any given day, how much does this vary? So you could take the past standard deviation, maybe blow that up a little bit, because, well, maybe the future is a little different than the past.
Absolutely.
And that would make a reasonable prior. But people get too uptight about these priors. Like, because usually if you have a decent amount of data, it's not going to make much of a difference.
Fair. All right. I derailed you. So now we're going to go into Frequentist.
Frequentist. So Frequentist Inference is based on the idea that we set this thing we call a null hypothesis, which is just like, often it's that the A and the B perform the same. But we could have other null hypotheses, like, in most A/B testing settings, it's that all the different recipes perform the same. So that's our null hypothesis. And then we work out how likely is it to get the data that we observed under that null hypothesis. So that, I don't know that that's that informative. Actually, it's super confusing, and most people don't understand it, even if they've taken 3 statistics classes. But yeah, that's exactly what you're doing. And if you want to be, well, we'll get into the pros and cons in a minute. I'll tell you how to be a snarky Bayesian if you want to.
So everybody gets the opportunity before you leave today to learn how to be a snarky Bayesian. I think that's fair.
Yeah.
All right. Well, let's move into the pros and cons.
Sure.
So there are benefits and there are drawbacks.
So on the frequentist, let me start with the kind of negative things about frequentists.
Shocker. I'm shocked.
What was that?
I'm shocked.
No, I'll tell you the negative things about Bayesian too. Sure. I think this is so with frequentist stats, it's the calculation of the probability of getting this data set is kind of for a fixed sample size. So you really shouldn't look at the data, you shouldn't peek, you shouldn't analyze the data on an ongoing basis, or you're gonna muck up those calculations, is basically it. So you shouldn't peek at the data. You definitely shouldn't look for a case where like on this day, all of a sudden the A and B got different. Now I'm going to stop the test. That's bad. That actually messes up it messes up the underlying, it's like putting diesel fuel in your gas engine. It's going to mess everything up.
Hold on a second. Does everybody on the call get that? If you're running Frequentist stats, with which the bulk of A/B testing tools are using, if you peak, you've put diesel in your car that's not a diesel. It really does mess up the stats.
Yeah, it's in a way that's persnickety and you wouldn't notice. But so I've been working on, I have 2 papers right now with a guy named Ron Berman. And he has another paper that I didn't work on, but the paper is, he took a bunch of A/B tests from a major A/B testing platform that you guys all know the name of, begins with some letter. I won't get that far, but
yeah.
He has his data from a major, he has about 2,000 A/B tests. And he checked to see, are real A/B testers likely to stop tests on a day that they pop significant, on the first day that they're significant? And, thanks, Dylan, for posting the link to the paper. This is called p-hacking, and what he computes is the false discovery rate, which is the rate at which people declare a winner when actually they are the same. And he calculates that about 1/3 of A/B testers are doing this. So it's not everybody. Some of the people, probably all the people on the call, are like knowledgeable about this and wouldn't do it. But about 1/3 of people using this platform are doing this kind of p-hacking, and it increases their false discovery rate. I can't remember, but it's a big, by 20% or something. So I'd have to look at the paper to get the exact number.
All right, false discovery rate.
Yeah, another, you want me to define that? That's the chance that I declare A is better than B or B is better than A when I really don't have enough data to conclude that. So as I poured the diesel fuel in the gasoline engine and I'm making mistakes because of that. How many mistakes am I making? That's the false discovery rate. So.
Right, and this really, really matters in the business world because you're making decisions that cost money. And you're either deciding that something is a win or that something was a loss, and you're losing out because it's not valid.
If it costs money.
If it costs money, that's fair.
That then Dylan will know. Okay, if we're talking about hero image on the homepage and we've got the 2 images and it literally is just click to deploy, then the false discovery rate is not as important because so what? I declare that this hero image is better than that one when they're truly the same. Well, I have no harm, no foul. Right. But if it costs money and engineering time to deploy this thing, then it becomes critical.
And this is probably a good time. He's not even here to hear it, but Matt Gershoff has a blog post called First Do No Harm that talks about that exact situation where if there is no financial cost to being wrong, then maybe it's not that big of a deal. So it's First Do No Harm. I'll find the link and put it in the
yeah. And that he wrote right after we had a conversation on this TLC channel.
That's right.
My paper also, there's another paper that we're going to get to in a minute that also covers that same issue and is kind of written from that point of view. But we haven't talked about what's bad about Bayesian.
All right.
No, let me go back in the call stack. I had put on my list of things to tell you how to be a snarky Bayesian. So to be a snarky Bayesian, you put in your Twitter handle, the null is never true. So when you do this calculation, you're saying if A and B are the same, how likely is it to get this data? And then I'm hoping that this data is different than what the null would tell me. So I'm looking for a mismatch, and then that tells me that A and B are not the same because it would be unlikely to observe this data under this null. But it's very much centered around this single null hypothesis, which always has to be A is exactly the same as B. You can't have a null hypothesis that A is about the same as B. Your null hypothesis always has to be like one thing, which is almost like two treatments are exactly the same to the 10th decimal. That's probably never true. And so Bayesians kind of dismiss the whole thing by saying, like, you're making all these calculations about something that's probably not true to begin with.
It's never true.
So but that's like a subtle point, and it's just how you be a snarky Bayesian. But if someone has the null is never true in their Twitter handle, but they don't say they're Bayesian, they're signaling to other Bayesians that they're Bayesian.
Oh, I see.
So, all right, what's wrong with Bayes? Well, these damn priors. You already started asking me, like, how do I set these priors? What do I do with the priors? And that is the main criticism of Bayesian methods, is that you have to, the whole engine doesn't work if you don't have a starting point. And so that starting point is like, and it's subjectively determined. And so people don't like Bayes, because if you do a Bayesian analysis and I do a Bayesian analysis, if we start with different priors, we're going to get different answers. People don't like that. I say, as a Bayesian, I would say, well, the priors are part of the analysis, and I have every right to question your priors. Just like I have a right to question whether you've picked the right response variable for this test. Like, you have to pick a response variable for a test, and we could kind of debate which one would be best for this test.
Right.
We can also debate what's a reasonable prior. And so anyway, that everybody hates Bayesian because it's priors, except people like me who are Bayesians say, like, well, there's so many other subjective things. What are you all uptight about that for?
And I've heard another criticism.
What's that?
Risk mitigation.
Risk mitigation. How so? I'm not following.
For risk with confidence and power. It's more around your sample size calculations.
Yeah, okay. So this actually raises, like, I had sort of 3 key points I wanted to hit. And yeah, we're half an hour in, and I'm at the 3rd point that I wanted to hit.
Awesome.
Which is, so when you set up your analysis, the statistical analysis has kind of baked into it a goal. So not only is the inferential engine different, but they also kind of have a traditional goal, frequentist versus Bayesian. So typically the goal in a frequentist hypothesis test, like, you know, P times 1 minus P and some Z value, and you do that little formula thing, or you find an online calculator for it, it has baked into it that there's 2 kinds of mistakes I can make. I can say that A and B are different when they're not. They're actually the same. That's type 1. And I don't know why they have these numbers 1 and 2. It's kind of stupid, and it took me forever to remember which one was which. But the one mistake is I say they're different when they're truly the same. The other is I say they're the same when they truly are different. And so when you set up your frequentist analysis and you set your sample size, you set it to achieve specific levels of type 1 and type 2 error. And we almost always pick those to be 5% for type 1 and 20% for type 2, which is really bad. Actually, it's kind of good for science, because science, you don't want to put something into the scientific literature if you're not pretty sure that it's true. Right. So that's why they go for, I don't want type 1. If I say this medicine works better than that medicine, I want to be pretty damn sure that's true. So I set my type 1 error at 5%. And if I miss, like I make a type 2 error, would be I say that this medicine is not better than that medicine, when truly one is better. Well, that's not as big of a mistake in science, so they make the chances of that. And that blog post you were talking about from Matt Gershoff is really about thinking about, like, well, in my specific business context, what do these mistakes mean, and how will they play out in the organization? And one might be really expensive and the other not so much. It could be that neither of them are that important, but I should think through that. And when I do my sample size calculation, I probably shouldn't accept these standards of 0.05 and 0.2, I should probably think that through, and how those work. Another way is to actually just think directly about how I'm going to make a decision and how much money that will yield me. So the link to the, someone posted, you posted in the Slack, the paper that I wrote. So the first paper that's posted in the Slack is Ron and some other people. The second paper is me and Ron. And in that paper, we say, well, what if you set this all up to maximize profit? I know I have a finite population of customers. When I run the test, I'm actually, by definition, giving the wrong treatment to some people. If one is better than the other, then some people are getting the wrong one. And then I'm going to make a decision of which one to do, and I could make a mistake there. I could pick the wrong one. And then all the rest of the people are going to get the wrong one. But there's only a chance that that'll happen. Usually I'll pick the right one. We actually look at those two costs and trade them off optimally. And we call it profit maximizing A/B test. And we just like completely abandon the type 1, type 2 error and say, let's just think about like how much money we're going to make, and start thinking about, you know, how sure do I need to be? Well, that's this trade-off between, you know, if I only have 100 customers to play with, I'm going to want to make my test really tiny because I don't want to give like 50 people the wrong thing. So I'm going to make my test sort of tiny, and then I'm going to make mistakes in which one to deploy, but mostly I'll get it right. So that's what that paper is about. And I encourage you to, if anybody's like really interested in that paper, email me, because like I just spent the last year of my life working on it, and
It's
I'm really excited about it.
I've probably read it through 3 or 4 times since I got it last month.
Uh-oh.
So it's fantastic.
No, then it's not written well. It should be easy.
No, but there's math in it, guys.
There's a lot of math in it.
There's some calculations.
Ron is like really into the math. And I was super excited because one of the derivations, so Ron did all the derivations, and I checked them. And like the core idea was mine, and then Ron did the derivations, and then I was checking his derivations, and in one of them, there's an arctangent. And I was so excited because my daughter is taking trigonometry, and I could be like, hey, look, arctangents are real. And she's like, no, what you do isn't real, Mom. She wasn't impressed, but she does know what an arctangent is. So, but if you,
part of the way there,
if you just read the introduction, you'd get the basic idea. And I'm looking to write more accessible versions of it, but I haven't gotten around to it yet.
We'll get there.
Yeah, and I'm also going to make it provides an alternative sample size calculation that's based on maximizing profit. There will eventually be a calculator online.
Just to add a high level summary for those that might be interested in this, if you've ever heard of a multi-arm bandit, the profit maximizing AB that Ellie and Ron recommend or talk about in this paper is essentially a way of doing that yourself, and it's pretty cool. Some pretty awesome.
Yeah, it's like doing one round of a bandit,
right?
But not so in a bandit, then you do it over and over again.
Adjusting, right?
That's kind of the power of Bayesian, is that you can do this stuff over and over, or you can just do it once. Like it doesn't matter.
Right. Whereas if you know right away that this is better than that, why have a holdout group that continues to evaluate it? You can just switch to the win.
Yeah, so we call it test and roll, which is roll is the switching to the win. Just go for it. Awesome. What's the next question?
Let's go on. All right.
Do we have questions from the audience? Like I think
good question.
Like I hope we didn't go down a rabbit hole of stuff that I'm only interested in.
It's not only you. If anybody has questions, pop them in there. In the meantime, we'll go to the next question here about when and why you might use Bayesian or Frequentist differently in relation to testing. So I know we've talked about a little bit estimating runtime and runtime calculations. Do you want to dive in?
Yeah, so it turns out that if you look at this, it's not really Bayesian versus Frequentist, but if it's like type 1 and type 2 error versus profit maximization, that the profit maximization stuff gives you much smaller sample sizes. Much smaller, like in some cases, like a factor of 10 smaller. And the reason is if you've got a limited, say you're coming up to Christmas and this is only a Christmas promotion and we want to decide, which of these 2 promotions to offer during Christmas. Well, I know that come January 1st, this is over. And so there's only so much traffic to play with. And so this paper is good when there's a limited population. If you're making like a major site design change that you're going to roll with for years, maybe, or like a branding change for a brand, then I would probably want to go back to the type 1 and type 2 error type stuff where like I'm just really damn sure that I've done the right thing. And the sample sizes, the runtime will be longer because you want to make sure that you're doing that. So that's
right. Another good example that I've seen on the, minimizing risk side is if you're going to pay for a recommendations engine to replace a different one. So there's a cost.
Yeah, that's a really good example. So in the paper, when we're looking at this, we assume that the roll cost is 0. Right. So once you've got it well enough to test it, that's good enough to deploy it, which is not always true, right? So if there's a like the example you give of, I'm deciding whether to swap one recommendation engine for the other, and I actually have to pay the vendor for that new thing. Then definitely you could actually incorporate that into a Bayesian analysis, but it would tell you run longer because you want to be sure, because you want to make sure that money is worth it. The other kind of funny thing I was talking about with someone yesterday, also I visited a website testing platform yesterday and was talking to their data scientist, and he had read the paper and was like, yeah, there's kind of like this org management problem. Like I read your paper and from the perspective of a company, it makes sense to just do what maximizes profit. But if I'm the testing manager, I have to prove out results. And I have like I need to tell my boss that like we deployed these things and I'm sure they were right. And there's like kind of a punishment organizationally for having done something wrong if you get caught later. Right. And so like, I think we should all step back and go like, well, is my job to protect my job or is my job to produce profits for the company? And so sometimes I think we might be over testing as a CYA strategy. Like we oversize our tests and we're trying to be super sure more for CYA, like the company, like
testing for risk mitigation.
Go fast and break things.
Yep.
Facebook says go fast and break things. It's okay to make mistakes. It's okay to deploy the wrong thing. But if you're at a very traditional company, it's not okay to go fast and break things. And so people like, I think are sometimes like, might like the Frequentist runtime calculations because they run it a little longer and you're a little bit more sure that you're right.
Or sometimes
but you are losing money. You are losing money when you do that. So that's sort of the trade-off there.
Sadly, what I see mostly in the industry and with our clients is a need at the higher level because they've been using the words wrong for so long, and they talk about their controlling for type 1 error as confidence, and they think of it as like I am confident in my results, and that's just a fundamental misunderstanding. And so they say, well, there's only a 1% chance I'm wrong, or a 5% chance I'm wrong. And it's not what it is.
It means that under the null hypothesis, there was a 1% chance of getting this data. That's what it means. Full stop. Nothing else.
Yep.
Whereas if a Bayesian tells you there's a 1% chance that B is better than A, that is actually what that means.
Right.
So
right. And there's this fundamental misunderstanding that they're making the same assumptions in both groups, and they're not. And so what's happening is they're calculating impact and then annualizing it, and they want to be very, very confident in that number because often it'll go in the P&L. And that's
Okay.
where that's happening.
Yeah.
You have all these people who want to minimize the risk of being wrong, so they're having to calculate
Or so
extremely
we could.
long
So
runtime.
you know what we should do, Kelly?
Let's do
We
it.
should write a new paper that's not called profit maximizing A/B tests, but it's called precision maximizing A/B tests.
Ooh, I like
And that
it.
would be something different. And
Yes.
if our goal was to make sure that our forecast was as precise as possible, then we would run tests longer.
Right.
So yeah, I guess I'm really annoyed by the state of practice, because we've got these calculators online that say, here, just do this, and without thinking about what all these things mean, and they set your type 1 and type 2 error for you. In fact, like sometimes there's not even a field to put those in. They just say, oh, I'm sure you want 95% confidence, I'm sure you want this.
Right.
And it makes it seem easy, and it makes it so that you're not thinking about the things that are really important, which are, what is the cost to deploy this thing? Is this an easy deployment that I could always change if it turns out to be wrong? Or is this like, we're betting the company on this, we got to be sure? Do I need a precise forecast, or do I just need to pick the right one? Or does the boss want to know A is better than B, or do they want to know that
How
A
much
is
better?
going to produce conversion rate of 20.2%? Like, those are different. Those are actually, getting back to how we started the call, those are different statistical inference questions. So when you ask the question, do we have enough data? It's, do we have enough data relative to the decision we're actually going to make? And different types of decisions require more or less data, right? I don't know. At a high level, think about it like, kid comes and says, which dress should I wear to the dance? And both dresses look cute, and it doesn't really matter, like, whatever you want, dear.
Unless you look at the cost of the dresses.
Oh, unless one of the
If you have to buy them.
Let's assume they're free. They're already in the closet. It's which one do we wear?
Doesn't really
That's a
matter.
different decision
Yes.
than, Mom, should I wear jeans or a suit to my college interview? Right? Like, these are different decisions with different implications. It's more important in the latter case to get right, because if you go to a dance and everybody thinks your dress is stupid, well, you'll go to the next dance and it'll be better. So, whereas college interview, you only get one shot at that. So I think people need to think about, what is the decision I'm trying to drive, and does the data support that decision? Without getting all into the statistical mumbo jumbo, I think your intuition will get you, that'll get pretty far.
Yep. So two things. First of all, Tim put in the TLC calls the sample size calculator that we developed after the last time we all talked. And one of the things that it includes, like Ellie says, is, all of the other sample size calculators pretty much that you can find out there default to that 95% and 20% and very limited ability to change them. And one of the things that Tim did when he created this was make sure that you could actually make a bunch of adjustments on there and see the impact that they have on your sample size. And it was really for the purposes of understanding. The calculator itself is, as useful as any other calculator, but it's really much more for education purposes for yourself and for your stakeholders. So take a look, and if you got questions, let us know. And then, yeah, no kidding, Ellie. And then Dylan asked in the Zoom chat, can we talk about the scientists? Oh, already done. Prior.
I don't know what Dylan was referring to there. I'm confused.
I think he's talking about what we were just talking about. He just put a name on it. The difference between. Go ahead, Dylan.
I would just say the scientist practitioner model is taught in industrial organizational psychology, and it's all about how do you balance science with practicing and applied the setting of business. And you guys already did a brilliant job. You just didn't call it that. So thank you.
Thanks.
Okay, now I know a new thing to look up. Thank you, Dylan.
All right, let's move on because we got about 10 minutes left. And we're going to, we just talked about that. Yay.
We talked about that.
And let's go.
But how do you estimate runtime for non-conversion rate metrics? I find this question so funny because, and it's the difference between learning on the job and learning in school. So when you learn in school, we actually teach you the runtime formula for conversion rate metrics, non-conversion rate metrics like AOV and RPV. we would do that first. And it's
Right.
called the difference in means hypothesis test, and the sample size for the difference in means. And it's z sub 1 minus alpha over 2 times the square root of s1 squared over n1 plus s2 squared over n2, the square root of all that, right? And yeah, you got that. Okay, maybe not, but whatever. That's the formula. And actually, the one that you learn for A/B testing for conversion rates is an approximation to that other one. It turns out that the standard deviation of a bunch of zeros and ones is the conversion rate times 1 minus the conversion rate. This is called the binomial approximation. But it's just like a trick to turn. So you learn the formula for non-conversion rate metrics first, and then there's a trick to turn that formula into the formula for conversion rate metrics. But people who learned it on the job were just like, I have a conversion rate and I need to do this. And so everyone in the A/B testing community learns the conversion rate one first.
Well, let's be honest. Everyone in the A/B testing industry probably didn't learn the calculation. They're using the calculator.
Maybe not. It's not a complicated calculation. You know, I have a Google sheet that like I'll share with my students, and it's not like super, it's
rocket surgery.
Spit it out my mouth. So if I can spit it out of my mouth from memory, you can type it into an Excel spreadsheet or
absolutely.
a Google sheet. But let's give names for those. So it's called the difference in means hypothesis test and the difference in proportions hypothesis test. And there's actually a very nice Khan Academy video on both of those. So like if you want to see the math or you want to like make your kids feel like they should be studying their math classes, you could go ahead and look at those Khan Academy together. I like to do that. Yesterday I was solving my daughter's calculus homework in R. I was showing her how to do it in R.
Nice.
Kind of brings family together.
Yeah, so especially when you're doing their homework.
Difference in means and difference in proportions.
Perfect.
The version of that, if you just want to do kind of Bayesian analysis of an existing data set without a bandit, what you want to learn is the beta binomial model for proportions and the normal model. And I did say normal twice. Mm-hmm. There's a reason for that. So you want the normal model for continuous numbers like sales figures, AOV, that kind of stuff. And then you'd want the beta binomial model if it's a binary kind of conversion rate type thing. And then, so you think of those two quadrants. We got Bayesian, Frequentist, and proportions versus continuous numbers. And there's just like simple, like I literally have a spreadsheet where each of those is a tab. And the students learn. So I'll give them, I actually give homework exercises where you analyze the exact same data set, both Bayesian and Frequentist, and see that you get the same answer. If there's enough data, you get the same
super answer. Helpful. And we have like 7 minutes left. And the last question is the one that I summarized like 8 different people's questions because it was all basically the same question. And it's coming back to what you're saying here, which is that, you're in the middle of the test. Can you change how long, how much the sample size is when you can end the test? As Dylan jokingly said, I've reached significance. Can I end my test?
So,
and how is that different?
Let's take them one at a time, Bayesian versus Frequentist. So if you're a Bayesian, yes, you can absolutely do that. You can analyze the data. And actually, if you take the whole data set and put it together, or you slice it into 2 pieces. So say you put it all together, you start with a prior, you add that data, you get a posterior. Or you split it into 2 chunks. You start with a prior, you update once, that posterior becomes the new prior, you update a second time, you get the exact same answer. So you can do this as long as you want, which is one of the reasons like people have adopted Bayesian methods for bandits, because it kind of makes a lot of sense in the bandit framework.
Right.
So yes, it does not impact your priors because your posteriors become your priors. So you always start with the same prior. You shouldn't go back and change your prior. Your prior should be your subjective belief before you saw any data. And then after you start collecting data, then you use Bayes' formula to do those updates. And it's all good. So let's pop over to the Frequentist side. Is it reasonable to recalculate the estimated sample size in the middle of the experiment? Well, kind of not really, or you should like throw away that data. So you get 100 samples and you realize your conversion rate was way off. You can kind of think of those 100 samples as a pretest, and you can use that pretest data to reset the sample size prospectively. But if you're gonna like keep that in that initial data in your data set, you're gonna increase your false discovery rate unless you bend over backwards to figure out a way to account for you having done that. Which Optimizely actually has a way of accounting for you doing that. So there are ways to get around it, but for the most part, you should plan your frequentist experiment and then end it.
Right, and I want to point out or dive in a little bit deeper where you talked about this, because this is what people do, right? And unfortunately, what you described, which is, hey, you get 2 or 3 days in and you're like, oh gosh, I ran my sample size estimation based on an assumption that was completely off. I thought that we would see at least a 2% lift, and in fact, I'm seeing a 20% lift. And obviously, there's a lot of opportunity here. I want to shorten my runtime. So what Ellie's describing you could do at that point is basically stop, run the analysis, assuming a 20% lift, see how long you would have to run it, and then restart with new data. Don't use that old data, using that new 20% as your lift, as your minimally detectable MDE, minimal detectable effect, and then run it for that time period, keeping those data sets separate. Nobody I know does that in that.
You know what's so funny? So I grew up in conjoint analysis, which is a survey research technique. We did it all the time. We'd run, we called it the friends and family. So we were doing survey research. So we would send the survey links out to friends and family, collect the data, use it to
estimate
sample size calculations, because like they're going to be different because they're our friends, but they're not that different, and it gets us close enough. And then we would, call the survey research company and say, find us 200 people to answer this survey, or whatever our number that we needed.
Yeah.
So we did that we used to do that all the time. Then we got to the web and somehow we forgot that.
Somehow everybody forgets it, right? I mean, we in a prior life with another company, we would do what we called soft launches, where we only launched it to like 10%, and we would use that soft launch period, which was normally a couple of days, for our estimation.
And also that first couple of days might be bad data anyway, because like, who hasn't effed up a test?
Yeah,
right? Like
that's for quality control and for estimation. Yeah,
I mean, I guess with today's tools, it's pretty easy to not mess it up. But in the early days of web testing, you could like accidentally be showing both people the control, or there were all kinds of mistakes that would happen. So you'd run this like kind of soft version and then use that to plan the regular test in the frequentist framework. That's a great plan.
Yep. Well, we are at the end of the hour. If anybody has any other questions, feel free to reach out through email or Slack. I'll try to get them to Ellie unless she sees them herself first. I really, really appreciate your time. Thank you.
Yeah, happy to be here.
It's been awesome. I've learned like 20 new things. Thank you so much. And as I said,
I've learned like scientist practitioner, so I'm excited.
Right. Gotta go look that up. All right. Thank you, everybody.
Okay, bye.
And don't forget, everybody, next week, actually, I almost forgot, next week we have another call. Normally they're not this close together, but with the holidays, everything kind of got messed up. So next week we'll be talking to Gary Angel and Jim Stern, and they'll be talking about how the digital analytics industry got started and how it's changed over time. So don't miss out. Thanks, everybody.